Hello and welcome to another video. This time we're going to be looking at keyboard interrupts. Strictly speaking, they're not EZ80 interrupts, but they can be handled in the same way. If we take a look at what's happening, our main program is running. When somebody presses or releases a key, the VDP sends a chunk of data to the EZ80 via the UART. The EZ80 then sends an interrupt message into our MOS firmware. The MOS firmware has a UART interrupt routine. If it then finds that the packet of data sent to it is relating to keyboards, then it'll pass that on to our own keyboard handler. Only then does our keyboard handler routine run. And when we've finished dealing with it, control passes back to the MOS interrupt routine. And when that's finished, control reverts to our main program. Let's take a look at the example program. When a packet of keyboard information is sent to the EZ80, it contains 4 chunks of data, each a byte long. The first is an ASCII code of the key that was pressed, if a valid ASCII code exists. There's a modifier code, and that's if you're pressing something like the Shift or a Control key. The third item is the FABGL V key code. This can offer us more information. We can find out, for instance, if it's the left or the right Shift key being pressed, or possibly a character which isn't in the ASCII set. The last byte simply determines whether the key was pressed or was released. So, for example, if I press the A key, we can see the ASCII code, we can see the modifiers nothing's pressed, we've got the FABGL code and the fact that the button went down. And if I let go, you can see it was an up message this time. So if I press the Shift key, we can then see that the modifier code is pressed and there's a GL code, but there isn't a valid ASCII code for simply Shift on its own. But if I press that with A, we then get the ASCII code, the FABGL code changes, and the modifier code is changed. So why might we want to use keyboard interrupts? Well, it means we get notified immediately there's a keyboard action. This means that our own code doesn't have to waste time constantly scanning the keyboard matrix to see whether a key is pressed or not. We can simply be notified when it happens. If we take a look at the code for this, it's actually pretty simple. In this example program, there's most of the usual features that you've seen in our other projects. At the start, we set the colours we want, the mode of the screen, and print the main text that's going to be on there. But the key thing we're going to be doing is setting up the keyboard handler. This routine tells MOS that we want to be notified whenever there's a keyboard event. Otherwise, we wouldn't know about it. And so here's the code to set up the keyboard handler. We load HL with the address of the routine that we want run whenever there's a keyboard event. We load C with 0 if we're going to be passing a 24-bit address, or 1 if it's a 16-bit address. And then we simply do a MOS call with parameter 1D. Later, when we've finished, we can cancel the keyboard handler by simply giving it an address of 0. When the keyboard event is triggered, the register DE contains a pointer to the structure of keyboard information that we discussed earlier: the ASCII code, the modifier keys, the V key code, and whether the key is up or down. So in our routine, we just did something very simple. All we did was grab those codes and print them to the screen. A neat little trick here is that we push DE and then pop the value off the stack into IX. This means that IX plus 0, plus 1, plus 2 and plus 3 are a quicker way of indexing the values of the packet of information which was sent. And for each one, we're simply tabbing to a place on screen, grabbing that value and printing it out as a hexadecimal value. Hopefully you can find a way of using keyboard interrupts in your programs so that you can get a quick response to any user interaction.